Cool. Before anything, let me tell you a story. This picture was shot for the movie Cleopatra, but sadly, it didn't make the cuts. Still, I believe I know what this scene is about, and I recognize some historical references, including to a dinner party that had a profound impact in human history. Let's see. The plot is this. They are in Alexandria, 48 BCE. In the middle, we have Sosigenes, a Greek astronomer to whom we owe a great deal. I will talk more about his work later, but in this movie, he's the most trustful advisor to Cleopatra, who was having a power struggle against her brother and desperately needs Caesar's help to resolve the situation. Julius Caesar, the Roman dictator, then became Cleopatra's lover and made her Queen of Egypt. So, to celebrate her ascension to the throne, Cleopatra in real life threw this lavish dinner party described by the Roman poet Lucan in his book Pharsalia. Lucan tells us this. The room was the size of a temple. It was filled with a wonderful smell of exquisite food. Not only delicious, the food was colorful with exotic birds and fruits serving golden platters, the water in crystal ewers, and the wine in jeweled goblets. But he also says that Cleopatra was dressed to impress, but still, what really caught Caesar's attention that night was an old wise man by the name of Acoreus. Not Sosigenes, but perhaps there is a reference here, because Acoreus talked a long time about astronomy, the floods of the Nile, and the relation between these two and the Egyptian calendar. That might have been an aha moment for Caesar. Look at his face. So that when he returned to Rome, he hired Sosigenes to lead the much-needed reform of the very messy Roman calendar. And that finished the first story of my presentation. My name is Cassio Neri. I'm a PhD in mathematics, former professor at university, and currently I work in finance in London. In the next hour or so, I'll talk about calendar algorithms. And along the way, I will cover topics and take decisions taken hundreds or even thousands of years ago that deeply impact the performance of these algorithms on very modern CPUs. This is a research collaboration with Professor Lawrence Schneider of EM Lyon. And my part of this work was carried out in my spare time, has nothing to do with my current or previous employers. I'm here in a personal capacity, and all the opinions that I'm going to express are mine and do not necessarily reflect that of my employer. So, I'm going to cover 4 algorithms, and we are going to spend more time with the most complex of the 4, which is this. Digital devices, including my humble Casio watch here, they display date and time in fields like this, but that's not how they internally keep track of time. So let's take a closer look. Usually, they keep a counter of ticks since some specific point in time. For instance, in this slide, we are counting the number of seconds since 0 hours of 1st January 1970. That's the so-called Unix epoch, as said by Ken Thompson, Dennis Rich, and other creators of Unix. The Unix epoch is also used by stud chrono system clock, but other systems might use different epochs, and also the resolution of the tick might change. So the question is this: how do we convert from ticks to dates and time? For the time part, it's easy. It just involves a bunch of divisions and modulus operations. And the working states, where in each stage we get the value of one field and the input for the next stage. And what makes this problem easy is the constancy of durations. Every minute has 6 seconds, every hour has 60 minutes, and every day has 24 hours. And also every week has 7 days. But sadly, this pattern breaks when we get to the date part, because the number of days in a month or in a year is variable. So the main problem we wish to solve is this. Given the number of days since some epoch, find the corresponding date. Of course, Lawrence and I were not the first to solve this problem. So let me contrast our solution to that of .NET 6. Here we are. Never mind if you cannot read the code, but pay attention to the slow moving parts, okay? I'm just showing this code to point out some programming constructs that harm the performance of these codes, namely branches and loops. This code also contains 2 lookup tables, and it is true that these lookup tables might help the performance of these codes, but the cache is a precious and very limited resource. So this code is competing for cache with other running pieces of software. So it's really hard to tell, but it is a possibility that overall the performance of your application degrades because of cache thrashing. And here is our solution. Again, never mind if you cannot read that, we will see that in detail later. I just want to tell you that it contains no branches, no loops, and no lookup tables. It's entirely arithmetic and involves basically a bunch of divisions and modulus operations. And they work in stages where in each stage we get the value of our fields and the input for the next stage. So it's no coincidence. It's very similar to what we do for times. And indeed, I'm going to present you a mathematical setting under which both problems, the date and the time problem, can be tackled in exactly the same way. It just happens that for the time part, there are further simplifications, but the mathematical setting is the same. So, but since I talk about performance, let me contrast the performance of these 2 and other implementations. But if I tell you, my code runs in 5 nanoseconds, that doesn't mean much, right? 5 nanoseconds is a very short period of time and is unreachable to our senses. And I want you to feel it. So this animation rescales time as if my code takes 5 seconds to run. Let's see how long the others take, and please bear with me. Seriously? Okay, finally, fine. I hope this was the most boring part of my talk and the entire conference. Okay, so let me elaborate a little bit further. And so those are the systems that use these algorithms. Some of them are just academics, and as you can see, our is in chrono, libstdc C++ chrono. It's also in 2 subsystems of the Linux kernel I implement myself, and then Sergei Pavlov implementing C# for the .NET framework. It has been released with .NET 7. So, having seen the performance, now let me talk about the overview of this presentation and its 3 pillars: the history, the maths, and the coding. I'm gonna start with the fascinating history of the Julian and Gregorian calendar. And especially for the Julian calendar, my main reference is the classical work of Saturnalia by Macrobius. There are other classical references, but they diverge between them. So there is still a lot of debate among historians about what really happened. And then I'm going to move to the math side, and I'm going to introduce this mathematical setting under which the 2 problems, the date and time, can be tackled in exactly the same way and involve integer functions of this form. And notice the division. If that division was the usual rational divisions between integer numbers, f would be called an affine functions. But here in that presentation, forward slash denotes Euclidean division, or integer division, if you will. And for that reason, Lawrence and I call this type of function Euclidean affine function. Then we're going to move to code and see some transformation that largely improve the performance of our algorithms. So starting with the history, let's go. It's very interesting and fascinating. So Romulus, the first king of Rome, is credited for this calendar. As you can see, the name of the months are quite familiar, and some even spell exactly the same in English and Latin, except for quintilis and sextilis. And actually from quintilis onwards, or from the 5th month onwards, months are named after their position. So quintilis means the 5th month, sextilis, the 6th month, September, the 7th month. So it made sense back then. It doesn't make today, but it made sense back then. What doesn't make sense in this calendar is that it only contains 10 months, account for 304 days. The remaining days of the year was part of the winter period. But since winter was a period of low activity, Romulus didn't bother splitting 2 months. What is even crazy is that the duration of the year, or winter, was not prescribed. It was decided by the pontifices, the high priest of Rome, and they were supposed to call the end of winter and the beginning of Martius and the new year close to the spring equinox to keep the calendar aligned with the seasons, okay? But then Numa, the second king, he split winter into Januarius and Februarius. He made Januarius the first month, and he changed a little bit the duration of a few months. And look at Februarius, the last month. It usually had 28 days, but every now and then it could have 50 or 51. So that the duration of the year could be 355, 377, or 378 days. There was a rule prescribing the duration of each specific year, but it was too complicated for the people, and the pontiffs, they just ignored the rule, and they still decide the duration of the year as they pleased. Then Februarius was moved to its current position by the Decemviri, the commission of 10 men who wrote the first Roman code of law. They might have some political and military reasons for that move, but from the algorithm point of view, that was a mistake, and we are going to deal with that mistake later. But what is really crazy here is that at that time, Rome was a republic, and the duration of the government was 1 year. So since the pontifices, they decide the duration of the year, they decide the duration of the government. So either by ideology or simply bribery, they abused their power, and at some point, the calendar got complete out of sync with the seasons. And that's the problem that Julius Caesar set himself to solve. And as I told you, he hired Sosigenes, and that's what the calendar Sosigenes come up with. So it's very similar to our calendar nowadays. Notice Februarius, it had 28 days, and every now and then 29. Every 4 years, every 4th year would have 29. The February would have 29 days. So that 3 out of 4 years would have 365 days, and the other one would have 366. So the duration, the calendar duration of the year will be 365 days and a quarter of the days. And in the balloon, I put the real duration of the year. It's quite close, not exactly, but quite close. But again, the pontiffs, they screw up, they didn't understand the rule, and they applied that to every 3rd year. So they made every 3rd year a leap year. So soon after, they realized it was again misaligned with the seasons. So Augustus Caesar and the Senate, they first renamed quintilis and sextilis in honor to Julius Caesar and Augustus himself. They suspended the leap years for a while until the calendar got back in sync with the seasons, and since then, the rule was correct applied. And despite these small adjustments made by Augustus and the Senate, that calendar is still called the Julian calendar. And the error of this calendar is about 11 minutes per year, which doesn't sound much, but it adds up to 1 day every 132 years. So after 16 centuries, the error was quite noticeable. That's why the Pope, Gregorius XIII, called for reform, and he hired a mathematician called Christopher Clavius to lead the reform. But the main ideas of the reform came from another mathematician called Aloysius Livius. And Aloysius Livius decided to set the calendar year, the average calendar year, to that number, 365 days, 0.2425. And again, in the balloon, you can see the real number. It's very close, and it can get closer, of course, and some calendars do achieve that, but at some aspects of Livius' reform that made it brilliant, in my opinion. Let's see. So first, he looked at that number as a correction of the old rule. So 365.25 was the previous average of the year, the Julian average of the year. So then he subtracts 0.01 and he adds 0.0025. And these two numbers can be conveniently written as 1 over 100 and 1 over 400. Doesn't seem special, but that allows to explain the rule and to write it in very simple words as a correction of the old one. So a leap year is one that is multiple of 4, exactly as it used to be, but then there is this addendum, except those that are multiple of 100, but not multiple of 400. So now look at that. So we can see that the two rules, the Julian leap year rule and the Gregorian leap year rule, only diverge 3 out of 4 centurial years. And the first such year, after the reform in 1582, was 1600, which is also a multiple of 400. So it's the exception of the exception. So it was a leap year rule, a leap year in the Gregorian calendar, and it was a leap year in the Julian calendar. So for people alive at that time, they didn't see any difference. The only time, the first time they really diverged, the two leap year rules, were in 1700, 118 years after the reform. So people had plenty of time to adapt to the new rule. So I really love the clarity of the rule and the forward-looking, the preparedness that Aloysius Livius allow us to have. So, and that finished my crash course in the history of the calendar. I could spend here 2 hours talking just about that, but I know you are here for a C++ conference. You want to see code, you want to see algorithms. So let's bring it on. So that's a code from the GCC's manual. I love that. I am such a programmer, and I want to show you one example where that really illustrates that code. So the first algorithm is why a leap year? Very simple, and one line. That's the code that I found virtually everywhere. I look at is leap year is implemented like that. Anyone has an idea why this is so? What is the argument behind this implementation? No? No? Okay, so let me just rewrite this in terms of if and else. It's the same logic because this one uses short-circuiting of the logical operators, but it's easier to reason about if we see the if and else version. So the argument for this implementation tells that in 25% of the case, we have an earlier return. We just do one divisibility check and then we return. It's only on 25% of the case that we have to carry on with other calculations. But that's what I implement in GCC. It always does 2 divisibility checks. So for many people, that might be optimization. But then I measure. And I was surprised. I confess I was surprised that my code was closer to 3 times. I'm not saying 3%. I'm saying 3 times faster than the classical implementation that is everywhere. And I was surprised, why is that? Because the argument for the classical implementation ignores the cost of branching. So if you can see mine, it splits also the execution, it branches, but it branches in two paths, one with 99% of the time, and another one with 1% of the time. So it's much friendly to the branch predictor. The branch predictor can make a better job with our code than with the other code, the classical code. And there is more. We always do just one branch. The classical code, 75% of the time is one branch, but then there is another one. So sometimes it branches twice. Our branch just once. We didn't stop there. I changed the 400 with 16. There's not a bug. That's allowed. And I leave you the fun to prove that. If a number is multiple of 100, and pay attention that the last line is executed only when y is known to be a multiple of 100. And so if a number is multiple of 100, it is multiple of 400 if and only if it's multiple of 16. So this is a valid transformation. And obviously, divisor of a power of 2 is much cheaper to evaluate this modulus operation. But then, Eurycletus suggests, why not change just deciding the divisor of the second expression and do this? So we use the ternary operator just to decide the divisor of the second divisibility check. And I'm sure you all heard that despite the d in either case will be a power of 2, so we don't need to worry about the modulus operation of power of 2 because the compiler is going to change for us, use a bitwise AND trick, and we don't need to do anything. Unfortunately, not in that case. No compiler could figure that out, so we had to do it manually. So we wrote something like that. I did more optimization, but it's another story. So with that expression, with that code, all the major C++ compilers, they generate efficient branch-free code, not with the classical implementations that is virtually everywhere. So that's the first one. Now, second algorithm of the day, the last day of the month. So February is special, needs some special treatment anyway. But then for the other months, that's classical. Also, almost everywhere we find something like that. Small variations, but the idea is this one. Using a lookup table that gives the right answer. But so if you use a lookup table, remember that there is a competition for cache. So it might be worse somewhere else. And there is worse. This code, if m is not between 1 and 12, then we do out-of-bound access to the array, which we know it's undefined behavior, it's bad, it's not memory safe, C++ is bad, C is bad, blah, blah, blah. So can we do better? So that's why I'm implementing GCC. Again, February is special, needs special treatment, but then I came up with this cryptic code and be twiddling there, and I leave you the fun to prove that this gives the right answer when m is between 1 and 12. If m is not between 1 and 12, it produces rubbish, but is still well-defined according to the rules of the language. There is no undefined behavior in that code, okay? There was, my original implementation, there was an extra AND with 1 at the end, but then Dr. Matthias Kretz realized that we did not need this AND with 1 because of very fortunate facts about the binary expression of 30. So we could also remove that. And there is an alternative. So this code is fast and is safer. But there is an alternative that is also fast and safe, which is this one. And again, I leave you the fun to prove that that works. And performance-wise, basically the same. There's not much difference. But I want to point out that we have the very last line, 9 times n divided by 8, is the first Euclidean affine function of this talk. We are going to see plenty more. Okay, now we are up for some cool maths. Please bear with me. Don't go away. So I'm going to solve the problem, our main problem, given the number of days since epoch, find the date, but I'm going to solve it first in yet another calendar, the Egyptian calendar, the one that Aquarius explained to Julius Caesar, okay? So it's a very simple calendar where every year has 365 days, no leap year involved, okay? So suppose that any days have passed since the first day of year 0. That's our epoch here. And then I'm going to introduce three functions. Y of n gives the year of the date. The y circ of n gives the day of the year, or ny. And y star of capital Y gives the number of days before y. Okay? And pay attention also to the colors, but I will keep calling the function by the name for the benefit of those who perceive color differently. But I'm going to use this color consistent to those functions and the relatives that will appear and that bear the same relationships. So since every year has 365 days, that problem is very similar to the time problem. And probably you already figured out the three formulas for these three functions. But let's put the formula aside and let's try to understand the relation between these three functions in that graph here. It will help us understand the algorithm. So on the x-axis, I count the number of days since epoch. So 0 represents the epoch, and n is a number on this axis. Y of n, I'll put on the y-axis, very conveniently. And it's obvious that it's not just that particular value of n that yields the same value of y. There are 365 values of n that gives the same year. So it's easy to see that this function y of n is a step function, and the length of this step is 365. Now, y star of y, here in the bottom, it counts the days before year y. So this value is the n that corresponds to the beginning of year y. It's there in the graph. And the day of the year is the number of days from the beginning of the year to the date. So that's the difference between these two numbers here, n and y star. So that's the representation of y circ. Now, if we do the same analysis, but within a year, and we use ny as the input, essentially everything that I said for years also works for months. Let's see in detail. So, again, on the x-axis, I put the number of days, but now from the beginning of the year. And let me talk about the Egyptian calendar, the months in the Egyptian calendar. There were 12 months of 30 days each, so which accounts for 360 days. The 5 remaining days was not part of a month. It was a period called epagomenal days, similar to winter at Romulus time, so it was not part of a month. But we don't need to care about that. We can just think it was a fictitious month, a 13th month, okay? All we care about is find a number between 0 and 12 that represents that month, either real or fictitious. And again, so we know that ny days have passed since the beginning of the year. We introduce the three functions, m of ny, which gives the month, m circ of ny, which gives the day of the month, or simply day, and m star of m gives the number of days before month m. And the way we built the previous graph is exactly the same we built this one. The relationship between these three functions is exactly the same. And again, because the real months had 30 days, you might have already figured out the formulas for these three functions. But there's something interesting here. The number 5 doesn't appear anywhere. Only 30 does. And one way to see that is, look at m star. It counts the number of days before month m. The fictitious month with 5 days is the last month. So its number of days in the last month is never accounted for because we never go m star of m for m after the last month because it doesn't make sense. That's the last. So the lesson here is that a shorter month at last doesn't create any trouble for us. In that spirit, February is complicated only because it's not the last month. And we can blame the Decemviri for that mistake. If they have kept February the last month, we would have simpler algorithms today, but we don't. So we did one thing for year, and we did the same thing for month. And when mathematicians do the same thing twice, they try, let's generalize. And when we write code, right, when we see two things together, say, let's factor out, create a function, a class, and etc. So let's do that. Let's generalize that, and instead of talking about year or month, let's take about a period. So we introduce the three functions, f of n, which gives the period Q. So suppose that any days have passed since the first day of the first period. That will be our epoch now. So introduce fn, that gives the period, f circ of n, that gives the day within the period, and f star of Q gives the number of days before period Q. So the graph is exactly like the two that we saw before. But here, the only difference is that now we allow the steps to be variable, not to have either 30 or 365, but to be variable. That will allow us to apply these ideas to the Julian and Gregorian calendar. So the graph is enough for us to understand what is going on. But in the paper where Lawrence and I wrote, and we show all the formulas, they make sense, we prove all the theorems, we need more than the graph. So we have these equations here, and we use these equations, they translate everything that you see in the graph, translate by these two equations. But don't bother with the equation. I'm putting here just for completeness. We need that in the paper, but the mental model given by the graphs are enough for this presentation. So let's apply these ideas to the Julian calendar before going to the more complicated Gregorian calendar. So I recall the leap year rule is on the top, and here the step can be 365 or 366, and let's see what is the formula for y star of y, which I recall, it counts the number of days before year y. So a reasonable attempt is this. I take y, the number of years from 0 to y is y. I multiply that by 365, as if every year had 365 days, and I add a correction that accounts for 1 day every 4 years, that is y divided by 4, and we end up with that formula. There are two bad news here. First one is not a multiplication as used to be in the Egyptian calendar, and it's the equivalent in time, what the time problem would be also just a multiplication. It's a bit more complicated, but the worst news is that this formula is wrong. And let me explain why. So here I have a table of y star of y for y between 0 and 4. So the difference between two lines is supposed to give the number of days in each particular year. But for 0 is giving 365, but 0 is multiple of 4, so it should be a leap year and should have 366 days. So this is wrong. And also for 3, it gives 366 days, but 3 is not multiple of 4. 3 is not a leap year. So this is wrong, but we can figure out that our formula is off by 1. If the leap year rule was expressed like that, our formula would be correct. But that's not how the Julian calendar works. But no reason for panic, that's the fix. So that formula is correct for the Julian calendar. But bear with me, we can do better than that. We are not going to use this formula, we can do better than that. Okay, but I want to point out that the two formulas that we found for y star, they have the form of an Euclidean affine function. So it's time now to try to do more analysis on those functions and see what goes on. So in the general case, f has this form, but in the particular case, when a is equal to 1 and b equal to 0, that's the case when we work with times, and that's the case when we work with the Egyptian calendar. So f becomes just a division, f circ is just a modulus operation, and f star is just a multiplication. Now we want to find f circ and f star in the general case that bear the same relations as the 3 in the particular case. And these relations are those given by the graphs that we saw and given by these equations. But again, don't bother with the equations. But using these equations, we are able to prove, to find the functional forms of f circ and f star. And notice that f star is also a Euclidean affine function. So let's apply that to our calendars. But first, I want to propose something radical here. Let's reform the calendar, okay? Let's us reform the calendar. So, we don't have the powers of a Roman dictator, and we don't have the powers of a pope. But that's what we are going to do, and that's what Christian Zeller did in 1882. He introduced a new calendar, the so-called computational calendar. Okay, it's true, it's not a calendar used by any country, but it's a very mathematically convenient calendar. So what I'm going to do is, all our problems we are going to solve on the computational calendar and then map back either to the Julian or the Gregorian calendar. So just to give you an idea what the computational calendar is, here I'm picturing 2 consecutive years in the Gregorian/Julian calendars, y and y plus 1. And as usual, they are split in 12 months, number from 1 to 12. And I'm going to show the corresponding months and years in the computational calendar. So first and foremost, Christian Zeller fixed the chamfering mistakes, and he placed February at last. So the years are a bit shifted. They run from March to February, okay? From March to December, he kept the same numbers of the month, from 3 to 12. But since January and February are supposed to follow December of the same year, they take the values of 13 and 14. So that's the computational calendar. And notice, and one last thing, so the days which are not pictured here, they are 0 base. So the first day of the year, or the month, is day 0, not day 1 in the computational calendar. So with all that in mind, it's very simple to deduce this mapping here from the computational calendar, from a date on the computational calendar to the corresponding date in the Julian/Gregorian calendar. Now pay attention to the year that February falls on. The computational calendar and the Gregorian/Julian calendar are off by 1. That's exactly the problem we had a few slides before, when we tried to find y star of the Julian for the Julian calendar. What we end up finding was y star for the computational calendar. So that's the formula that we are going to use. The one that was wrong now is correct for the computational calendar. And let me be a bit more precise. I'm saying Gregorian/Julian, but actually there are 2 computational calendars. There is the computational calendar based on the Julian calendar, such that the leap year rule of these two are off by 1, and the same thing for the computational calendar based on the Gregorian calendar. So let's see y star again for the computational calendar based on the Julian calendar. So I insist, this formula was wrong for the Julian calendar, but is correct for the computational calendar based on the Julian calendar. And here is the leap year rule, exactly as we wish it was. Now it is. And if you equate the coefficients of this particular form of y star with the general form of y star, we can easily find the coefficients a, b, and d. And since we have a, d, and b, we have the formulas for the y and for y circ. So that's the year and the day of the year. So just basically divisions and modulus operations. Now let's go for the Gregorian calendar. Again, the leap year rule is off by 1 in the computational calendar based on the Gregorian calendar. And here again, a reasonable attempt for y star. Multiply y by 365 and do the correction. 1 day every 4 years, minus 1 day every 100 years, plus 1 day every 400 years. This formula is correct, but it is not an Euclidean affine function. So should I throw away our beautiful mathematical setting and try to generalize even further? Maybe, we can do something along those lines, but that's not what we did. What we did was we introduced the century. Actually, we are just acknowledging Lilius' idea that every century, every fourth century should get an extra day. We are just acknowledging what Lilius said we should do. So we introduce a century as a first-class citizen in this whole calendrical calculation business. Not all algorithms out there, they do that. They try direct to go to the year. We take a step back, let's find first the century and then carry on later. So we introduce the century, the leap century, those that had one extra day, and the rule is again off by 1 with respect to the Gregorian calendar. And then the exercise is the same. Multiply the number of days in a common century by C, add the correction, we find this formula. And the same exercise again, we compare that to the general formula of the star function, we equate the coefficients, we find the coefficients, and with the coefficients we find the formula for the century and the day of the century. So I'm skipping the details, I leave it for you. So let's take a step back and see what we got so far. So if any days have passed in the first day of year 0 of the computational calendar, so now our epoch now is the first day of the computational calendar, which is 1st March of year 0. The slide that we just saw gave us these two formulas for the century and for the day of the century. So NC counts the number of days since the beginning of the century. So NC counts days within a century. It never crosses a century boundary, right? And if it never crosses a century boundary, so the leap year rule in the Julian calendar and in the Gregorian calendar, they are the same, they match. That means the formula that we found before also applies here. Okay, it's the same formula. The only difference is now we use NC, which is the day within the century, and we get Z, which is not the year, is the year within the century, or the year of the century. But if we have the century and we have the year of the century, the year is just that, okay? So now, only the month and the day remain to be found, and the input for that is the day of the year, NY. So again, we start with the star function, M star. I'm putting a table here. It counts the number of days before M. So for March, which is the first year, there are 0 days before March. For April, there are 31 days before April, which are the 31 days of March, and so on and so forth. And notice that for February, it doesn't matter if the year is leap year or not. February might have different durations, but M star of 14 is always 337, okay? And it turns out that that M star is also no Euclidean affine function, this one here. There are some ways to get that formula, it's not out of the sky. We can find this formula, and then again, doing the same exercise, we find the formula for M and for D. So that's here, everything together. This is a full functional calendar algorithm for the epoch, which is 1st March of year 0. We have these formulas on the computational calendar, and when we have the Y, M, and D on the computational calendar, we map back to the Gregorian calendar. That's it. But there are too many divisions here, and they bother me. They bother us, me and Lawrence. So I'm going to do something about that. So we have solved 3 problems. Is leap year, last day of the month, and now find the date given the days after, any days after epoch. But incidentally, in the middle of everything, we also resolve the reciprocal problem to this one, which is, given the date, say 1G, MG, DG, so the year, month, and day in the Gregorian calendar, how many days there are between the epoch and that date. So how do we solve that? First, we move to the computational calendar. We map to the computational calendar. It's the inverse of the other map. And then recall that Y star on the computational calendar, Y star counts the number of days from epoch to the first day of the year. M star counts the number of days from the beginning of the year to the beginning of the month. And D is the number of days between the beginning of the month and the date. So N is just the sum of these three numbers. And here are the formulas that we found before. So here is the solution, our fourth algorithm, okay? But this one, again, has some divisions and they bother me. So what we can do about that? So what's my issue with division?
So before we get to the divisions here, that's a lot of history and mathematical history. I'm wondering how much of this was known to all the other algorithmic stuff, and what did you actually contribute to mashing this together?
Okay, so our contribution basically, some of the computational calendar, they are known. Okay, it's using the called Zeller congruence. Christian Zeller invented that in 1882, and Booth used that, libc++ used that. Okay, our contribution was just these relationships given by the Euclidean affine functions from y star getting y, from C star getting C, and the relationship between those functions, that's one of our contributions, okay? And you can see, for instance, this is here. This formula for M star, we are going to see on Boost and libc++, but not the formula for the century because they try to get direct to the year, and that helps performance, okay? So my problem with division is because it's the hardest of the four arithmetic operations. And not only for me, also for the CPUs. It takes far more cycles. If you remember what Matt Gottbold showed in his lightning talk, division is much, much more expensive, not just for us, also for the CPU. So I'm not good with mental calculations, but when I have to divide n by 5, I do this trick. I multiply by 10, divide by 5, which is 2, and then I divide by 10. And divide by 10 for me is easy. Divide by powers of 10 is easy because it's just a shift of digits. The same thing happens for the CPU, but if you use binaries, right? So here is how the CPU can calculate and divide by 5. Multiply by 2 to the power of 34 divided by 5, and then divide by 2 to the power of 34, which is just a bit shift. But unfortunately, 2 to the power of 35 divided by 5 is not an integer number. So the formula here is just an approximation. The big number that you see in the numerator is an approximation. It's rounding up to the near integer 2 to the power 34 divided by 5. So I'm rounding up. So the result is a bit higher than should be. But that when you use rational division, and we are not interested in rational division. We are interested in integer division, and the integer division truncates down. So maybe the error of the rounding up is compensated by the truncation down. And that's exactly what happened. Gregorian and Montgomery showed that in 1994, and major compilers, they apply this transformation. So you write that in your code and divide by 5. If you see the assembly code with optimizations on, you are going to see that it actually multiplied by this huge number there, and then it shifts by 34 bits. And that works for all numbers, all unsigned integer numbers with 32 bits, okay? There's something similar for integers, there's something similar for 64-bit numbers, but that's the idea. So let's see what it brings to our code, okay? So this is, for instance, a formula that we can find in Boost and libc++, and also MSVC-STL, okay? So we can see there are two divisions, but I just explained the compiler replaced those two divisions with a multiplication and some cheaper operations. And that, after that, the number of multiplication becomes a proxy for the performance of this code. So we counted the number of multiplications. This one has 2 very explicit and 2 after the Gregorian and Montgomery transformation. It has 4 multiplications. Also notice that in the expression for D, we use M. So there is a data dependency here. The CPU needs to find D, to find M before it can start D. So if we use our formulas, especially the alternative formula for fcirc, use here, using the modulus operations, now we have just 3 multiplications. One that explicit from the 5, and the 2 after the Montgomery transformation, Granullo-de-Montgomery transformation. And there is no more the data dependency between M and D. So the CPU can start the calculation of D before it finishes that of M, right? I'm lying. Unfortunately, the modulus operation, Granullo and Montgomery, they don't say anything on how to optimize that. So what the compilers do is they just use that expression on the right. And if I replace that expression back into the code, it gives a fair assessment of what goes behind the scene, what the CPU really calculates. And again, we have 4 multiplications, and the data dependency is back on. So we didn't make any improvement, not yet, because another contribution of us was to generalize the results of Granullo and Montgomery to Euclidean affine functions. For the particular function that gives the month, that's what we found. So, and as you can see, the division, the first division, the modulus operation, is by a power of, the divisor is a power of 2. So much better for the CPU. There is another division, but for the last division by 2141, we don't need the modulus. So we are okay just using Granullo and Montgomery. But when we need both, then our result helps a lot to improve the performance. After we do that, then now we have only 2 multiplications, not 4, and we broke the data dependency between M and D. As soon as N3 is obtained, the CPU can, and our modern CPUs, they do start the calculation of M and D at the same time, in parallel. So it speeds up a lot. So that's the final version. That's what is in GCC, in the Linux kernel, etc. But if you pay attention, you'll see that I didn't use our beautiful optimization result for Euclidean affine function in the first block for the century. And for the second block, we use half of that. There are 2 reasons for that. One is ugly, let's put aside, but there is another one that I find beautiful and I want to share with you. And for me, this is historical bit twiddling. Let me explain why. So I'm interested in these 2 expressions here, okay? So, and notice that NEC is something divided by 4. Let's call this something R, okay? And the expression for P2, I'm more interested in the part that is inside the bracket. So I'm interested on that. So if I replace NC in the second expression, so we conclude that at some point the CPU evaluates that expression. Let's think about that in binary. So here I'm picturing the bits of representing the bits of R as boxes, and I'm paying special attention. I'm highlighting the 2 rightmost bits or boxes. So first thing we do is we divide R by 4, which is just shifting 2 bytes to the right. Then we multiply by 4. We multiply by 4, which shifts back to the left and fill the gaps with zeros. And then we had to add 3, which in binary is 1, 1. And that sum, 0, 0 plus 1, 1, has no carry, so the result is the same as just taking R and making an OR with 3. So these 3 operations can collapse to just 1. And the good news is some compilers can even figure out by themselves. That's why we left as it was, because some compilers can figure that out themselves. But now here I'm talking some compilers later because of this work. I also took a look at C# compilers and Rust compilers. So some of them, some of the C++ compilers, they can, others cannot. So, and sometimes you have to do that manually to get the best performance possible. And why do I call that historical bit twiddling? Look at that. These 4 here, we can pinpoint that these 4 comes from Society's decision that every 4th year should get an extra day. And that was a decision taken more than 2,000 years ago. These 4 here comes from Lilius' decision that every 4th century should get an extra day. a decision that was taken more than 400 years ago. This tree here comes from the fact that the computational calendar and the normal calendar, they are off by 1 with respect to 4. And that's the invention, the computational calendar was invention by Zeller more than 140 years ago. And put everything together is our modest contribution from 2 years ago. And that's it. I want to thank you for being here. I want to thank all those people who helped me, especially my wife, Cristina Costa, and I'm happy to take questions. Thank you.